It's been a tough time for everybody in Hong Kong over the last year, and obviously not as much rugby or other sports as we would have liked. But spring is here, the vaccines have arrived, and I know there's a little bit of uncertainty and maybe some concerns in the community. So I've just put together this presentation to give some information about what this means for us in the rugby community, but also in Hong Kong in general. With any form of infectious disease, there's really two things that we need to know. There's the exposure risk and there's the host response. So the exposure risk is if you are never exposed to COVID or chickenpox or hepatitis B, you'll never get those infections. And this is the level that the public health measures work at. If you wear masks, if we have quarantine, if we social distance and people work from home, there's less people moving around the city, there's less potential events where one person can be exposed to the infection. It's sort of all about reducing the probability and reducing the exposure. And that's how the public health measures have been so successful in Hong Kong. The host response, that's what happens if we are exposed. And this depends on how fit we are, how old we are, and whether we have specific immunity. And so the public health measures work on reducing the exposure risk. Vaccination works by boosting our individual immunity to the infection. So immunity is resistance to an infection. And this picture, the orange ball with the fluffy bits on the outside, is a SARS-CoV-2 virus that causes COVID. And on the outside, the fluffy orange bits, those are the spike proteins. The white here are antibodies. These are like nature's soldiers. And these antibodies recognize the spike protein in particular, and they grab hold of it, and then they call their friends in, and they basically break down and damage the virus before it can do any harm to our bodies. They sort of work as a team, and we have a very complicated role in the immune system that helps to fight against these infections. When dealing with immunity, there's only two ways you can get immunity, actually. There's by naturally getting the infection and getting sick from it, or being immunized. Those are the only two ways. And people have asked me on a number of occasions, on the one hand, look, you've been reassuring us throughout this process that on an individual basis, the risks of this disease are not that great, and that is the case for the vast majority, especially for fit and healthy and younger people, such as in the rugby community. But some people will be infected and some people will be impacted. But in general, the risks are quite small. But we don't have any immunity in Hong Kong. And I just want to give an example. This is a map of England. And this is an example of what happened with the variants, but I think it's a good sort of way of thinking about the infection that we have in Europe and in the US in comparison to Hong Kong, where we don't have any. In the UK at this time, if you look at the top of this picture, it was the 10th of November, and at that time they were having thousands of cases. The yellow represents all of the cases that were occurring on that day were caused by the old viruses, the old variants. And the varying bits of orange going through to purple and then almost dark to black at the bottom right-hand corner, those were the new variants that start to develop in September last year in the southeast of England. I'm just going to play this because it's a little video, and I want you to look at the top, the date, as the date changes, and the infection burned through the UK. Over a period of about 6 weeks, this new infection just took over the whole country. And remember, we're talking there of a population of about 50 million, so 8 times bigger than Hong Kong in population terms. That's just England. But London was the inset. My oldest boy was working as an emergency doctor in London at that time, and the hospitals were overwhelmed. The system didn't break down, but it was taking 6 or 8 hours for an ambulance to be able to offload a patient into hospital because the hospitals were so busy. And that's what we're trying to avoid in Hong Kong. On the one hand, we don't have any infections, but the reason we have very strict public controls is if this infection did, especially the new variants, if it got into the housing estates of Hong Kong, it would burn through and it would do a lot of damage. And so we don't have infections, we don't have immunity. How are we going to get immunity? Well, the answer is through vaccination. And I want to give some sort of historical perspective here. I saw my first case of HIV AIDS in 1982, and we still don't have a vaccination against HIV. I saw my first case of COVID in late February last year, and we've got vaccinations which are incredibly effective. So it's an unbelievable, we sort of take this for granted, but it is an absolutely unbelievable achievement. And these are the studies that were ongoing in December. But there's actually about 280 trials registered on vaccination with the World Health Organization. So there are lots and lots of vaccines being developed. And they go through these, you've probably heard these descriptions of phase 1 and phase 2 and phase 3 trials. Basically of increasing numbers and checking on the safety, and then they get approved by governments, and then they get rolled out in smaller numbers. And one of the questions, and it's a very valid question, is, have the trials been rushed? What I would say is they've certainly been accelerated, but another way of looking at this is we've had pretty much the top epidemiologists, virologists, the top scientific brains on the planet have been working on nothing else with almost limitless resources over the last year because the world's closed down. And so the extraordinary impact on the economy, the pressure to get a solution here has been enormous. And we do now have safety data on hundreds of millions of doses that are being given. So it's true that these vaccines have been accelerated, but I really do believe that we have very good safety data. We know that really vaccine complications fall into two types. There are those that happen within a few days. This is the sore arm or the fever or feeling fatigued or having some nausea, or even having these more sort of significant complications like a significant allergic reaction. Well, we've got a really good handle on these now because we've given hundreds of millions of doses, and we know that they're not really any different to many other vaccines that we take for granted. We do also hear about the sort of longer term risks, and it's true we don't have a lot of long-term data, but we also do hear a lot of noise, and some of the media reporting honestly is not very helpful. There's reports about people who die after having had a vaccination, and I want to be clear about this. I think it's incredibly important that we investigate any concerns that are associated with vaccination. But people do die every day in Hong Kong, unfortunately. About 16 to 18 people die from heart attacks, and about 8 to 10 people die from strokes every day. So the reporting about somebody who had a vaccine 3 weeks ago and died today, and they're saying they died after having the vaccination. Well, this is what scientifically we refer to as confusing correlation and causation. It's like saying somebody's died since we had the last full moon. It doesn't mean that the full moon caused it, and it usually means that the full moon didn't cause it. But we need to be scientific and look at the potential associations. And likewise, we've just closed down the BioNTech vaccine for a period of time. I suspect that the safety data, when we get all of it through, is going to end up with the programs getting back going again. But it's right that we look at that. Just briefly, this slide is a description of how vaccines work. And there's a hexagon here. You can see there's 6 different corners, so to speak. But I'm going to look at them at the bottom 2, the middle 2, and the top 2. So the bottom 2, this is where you give the whole virus. On the right, you might give a live virus, but one that has been made safe to not cause disease in humans. We don't have these for COVID, but this would be an example of the measles vaccine is a live vaccine but doesn't cause disease. On the other side is an inactivated, so it's a whole virus, and this is the way Sinovac works. In some ways, it's an old-fashioned type of vaccine. It's obviously a new vaccine, and there's nothing wrong with being old-fashioned. It means we've got more sort of experience of these type of vaccines. So Sinovac and Sinopharm, they are killed. They don't cause disease, but because they are killed, they also don't produce quite so much of an immune response. And so when we give attenuated vaccines, we usually add something that's called an adjuvant. In the case of Sinovac, that's aluminium hydroxide, and that helps to stimulate the immune system to give it a bit of a kickstart, so to speak. The middle two vaccines work on the spike protein. Well, they actually, all of them work on the spike protein, but if we look at the middle, on the right, the subunit vaccines, like Novavax, which is about to be released in a number of places, and it's got some pretty decent results from trials. In that situation, they build a bunch of spike protein in a factory and then put it in injections and inject the spike protein into the body. On the left, these are the new super-duper RNA vaccines, and these vaccines really do represent an incredible leap forward in technology, and I honestly believe that they could be the single most important advance in medicine in my whole career. This includes the BioNTech vaccine, Pfizer in Europe and the US, and Fosun BioNTech in China and Hong Kong, and the Moderna and some other vaccines which are being developed in other countries. And the way that they work is there's a little bit of code that's made almost like a piece of computer code. It's put inside a plasmid, a piece of fat, and injected into the body. And this code goes into the outside of the cells. It doesn't go into the nucleus. It doesn't integrate with the DNA. There's many stories about, this impacts the DNA and is going to cause infertility or is going to cause complications in the future. Well, it's important to understand that RNA does not go into the DNA. The code effectively borrows the cell's factories to build the spike protein. And the piece of code only lasts for a few days. It gets broken down because it has a short half-life. So after a few days it's gone, but the spike proteins that it's coded for and built circulate in the body, and they circulate in quite high numbers, and that's how the vaccine works. The top two levels are, on the left, DNA vaccines. These are under research. On the right, the viral vector vaccines. I put these together because these both use a DNA model. What happens in the case of the viral vector vaccines, which is AstraZeneca and Johnson & Johnson, is we take a virus. In the case of AstraZeneca, it's a chimpanzee virus that doesn't cause disease in humans. We put a little piece of code inside that virus and inject the virus. The virus produces an immune response, and the code codes into the spike protein again through a number of levels, effectively going through the same sort of process. So in each case, we're building spike proteins. So this is a model of the virus, of the SARS-CoV-2 virus that causes COVID. The red on the outside is the spike protein. This attaches to the cells of our body, and it's through that the virus attacks and gets inside our cells. And the antibodies try to block this, and by blocking it, they both reduce it getting into the cell, but they also, as I described earlier, they bring in all their mates to smash it up and stop it causing any harm. So the majority of vaccines work. In the case of Sinovac, as I mentioned earlier, we inject the whole killed virus, but in the case of the other vaccines, we inject code which helps to build these little red bits, and the body recognizes those little red bits and builds antibodies against them. This is a very simple description. It's on our website if anybody wants to have a look. It's the 3 vaccines that are available in Hong Kong, and I'm using this just to show that what the health department made a decision early on that they would recruit 3 vaccines that worked in different ways, And this sort of made sense. I know there's a lot of politics, and we have to try. I'm a doctor. I keep out of politics. We have to try to remember that looking back a few months ago, the doctors who were involved in making these decisions were not sure which vaccines were going to be the most effective. So they sort of took one from the bottom, one from the middle, one from the top. And actually their decisions have been shown to be good. I'm just going to talk a little bit about how immunity works and how immunization works. It actually works in two ways. It works, firstly, directly, and it works what we call indirect or herd immunity. So, direct immunity, this deals with the question, if I get an immunization, how less likely am I to get seriously ill or die from this disease? So this is all about the benefit to me. I take the vaccine, what benefit do I get? And the good news is all of these vaccines are fantastic on an individual level. They all stop people dying, and they reduce the chances of going to hospital and going to intensive care. So they're really, really effective vaccines. The second question is, if I get injected and have immunity, if lots of people do that, can we protect people who haven't been immunized? Can we look after other members of our herd, so to speak? Maybe those who couldn't get vaccinated, like children, or maybe mums who are pregnant, or people who have medical conditions that mean they can't have vaccination. And we know that if we can get up to about 2/3 of the people in a population to be vaccinated, that the epidemic actually starts to die and go away. And this is a sort of model way it does this. The green in this case are people who are vaccinated. And you can imagine that as a person is bumping into somebody and potentially infecting them, you can see how the green in this case have protected the susceptible individuals on the outside of this cluster, because they've acted as a sort of break, and the infection doesn't have enough ways to travel around the city, and eventually it gets bored and disappears. That's at least the plan. That's how herd immunity works. That's why we vaccinate children for measles and for other forms of infection. So when we're vaccinating people, it's a little bit more complicated than just giving a vaccine and does it work. We need to understand how it works, but also how it works in different situations. And this is a bit of a sort of a complex slide. It's actually an easy concept. There's efficacy. Efficacy is how well something works, but only when we do it in like a medical trial in a very specific circumstance. And I think, everybody is aware of the fact that the BioNTech vaccine had 95% efficacy in a particular trial, and most people are also aware of the fact that the Sinovac vaccine was reported as showing 50-something% from press reports from Brazil. The problem with that is these trials all measure different things. You see, a vaccine, if we look at the left of this, a really fantastic vaccine might actually stop transmission, so it would stop anybody getting infected. But a good vaccine might allow some people to get infected, but they just don't get sick from it, or maybe they get sick, but they don't get really sick and they don't have to go to hospital. So vaccines sort of work in different ways, and one way of thinking about this is they all push somewhere down this pyramid from the top, and what we know about the vaccines is that they're all good at pushing far enough that they go past severe disease and past mild disease towards sort of asymptomatic infection. How good they are at stopping any form of infection, we didn't know, and the efficacy studies weren't designed to answer that question. So again, it's a bit sort of it's a complex and nuanced, but you can't compare the BioNTech studies that showed 95% and the Sinovac studies that showed 50%, or it was like 90% in one of the studies in Turkey, and then it was a little bit less in Indonesia. And of course, people look at that and naturally go, "Oh, that's a bit suspicious. They're all different results." But actually, from a scientific point of view, it makes sense because they're all measuring different things and they're doing different studies. When we get into like the real world and we give these vaccines, then we measure what we call effectiveness studies. It seems a bit, it is being a bit pedantic, but efficacy studies were very small. They were like 30 or 40,000 people. But we've now given hundreds of millions of doses. And we can now look what happens when we give the vaccines in the real world. And the answer is the vaccines are absolutely fantastic. It's like they're almost better than we hoped they could be from the early studies that we looked at. And so, for instance, this study, the Siren study in healthcare workers in the UK, shows there's an 86% reduction in symptomatic infection after the second shot. The same in Israeli healthcare workers. We have lots of fantastic data from Israel, and that's exclusively on the BioNTech vaccine. But what's really important, these studies have also, in the healthcare worker studies, have shown that there's a significant reduction in the families of healthcare workers when they've been vaccinated. And this is important because we know that healthcare workers are at greater risk and their families are at greater risk. And so we're now getting evidence that not only do the vaccines reduce disease, but they do reduce transmission, and they seem to be reducing transmission quite well. This was a fantastic study in Scotland that showed 85% reduction from the BioNTech and 94%, and this was a reduction from AstraZeneca, and this was especially in elderly and vulnerable patients. And so if you look at the population data from places that have done a lot of vaccinations, especially Israel, from the UK, and now from the US, what you're seeing is when people are vaccinated, they basically don't die, and the healthcare system stops being overwhelmed, and we get a real benefit in population terms. So these vaccines are really, really effective. This was a study from Israel. We don't need to go into too much detail, except to point out, this was a study on 600,000 people. So I mentioned the BioNTech, the Pfizer study, the original, was only 44,000 people. Most of these studies, the efficacy studies, were 30, 40, some of them even smaller than that. This is on hundreds of thousands and millions of people. The effectiveness studies tell us that the vaccines are really, really fantastic. So the key message is vaccines are really good. They work. There is no question. They're highly effective. We know that they're safe, certainly in comparison to other vaccines. Now, I'm naturally cautious. I think it's very reasonable that somebody who's young, and we know that COVID is much less serious in young people. It's perfectly reasonable that somebody who's young is a bit more cautious about vaccination. There is a question about how significant long-term COVID can be, and this is a new thing that we're beginning to understand and research. But there is more to COVID, and whether it kills you or not, it can also have an impact on individuals and health systems. But for sure, we know that COVID is a more serious disease as we get older, and so young people could perfectly reasonably wait. We have a very low disease prevalence here, but that means we have very low levels of immunity. So, if we want to get back to normal, whatever normal is going to be in the future, we need high levels of immunity, and the only way we can do that really is by getting a lot of people vaccinated. Challenges? Well, the biggest challenge in international terms, and certainly in Hong Kong, is vaccine hesitancy. And there's a lot of skepticism. We know that in population terms, the most important thing in driving vaccination is trust in government. And of course, we are playing this out against a political background which creates a lot of uncertainty. We don't know how effective these vaccines can be in achieving herd immunity, and we don't know how the impact the variants are going to have, because the variants are more infectious. The UK variant is anything between 50 and 100% more infectious, and that's why we are worried about, as in the map that I showed you earlier, about this variants getting into Hong Kong and burning through. And that's why I think Hong Kong is not going to relax border quarantine until we have a much better handle on the variants and higher levels of population immunity. We're not sure which of the best vaccines are going to be. I think at the moment in Hong Kong we have a choice of vaccination, and So the vaccines are very, very good, and you make your choice on the basis of evidence. We do have lots and lots of evidence, especially evidence from the BioNTech vaccine, because it's been given so much in other populations, in hundreds of millions of doses. We have a lot of information about safety, but there are valid questions about things like, breastfeeding or thinking about having a baby. And it seems likely that the vaccines are going to be safe. The advice in Hong Kong is not quite so clear. In Singapore, the advice is that you should complete your vaccines and wait for at least a month before trying for a baby. But you could equally say, why not give the vaccines to the rest of the population, and we try and protect the young mums and potential mums through herd immunity. So I don't think anybody should feel any pressure to have a vaccination. Can we mix different vaccines? Probably we can, and I suspect what we will be doing in the future is giving booster doses probably once a year, and the boosters will probably be engineered to account for the new variants, because we can now identify the viruses as they change. These viruses change all the time. It's like a fingerprint, and it's about 30,000 blocks in a virus, and every one gets made. Almost every one has a tiny little chink or change from the previous one, and some of these changes are biologically important, and we can identify that now, and we can start to build vaccines for the future. So I think the new technology is fantastic. It offers a great potential for the future, not only for COVID, but for other infections. And as always, there will be many positives that we will take out of this as we look forwards and we build to the future and get back to playing the game and get back to our teams. So that's an overview from my perspective. There may be other questions that I didn't answer, and if there are, feel free to fire those over to Lucy, or to talk to the physios and anybody in the medical teams around your team. I'm more than happy to try to answer any of those questions, and we can put a Q&A up on the website, or if you think it's of any help, if there are any other areas around COVID that you'd like to have some information, more than happy to try to put something together for that as well. So that's a summary from my perspective. You know that I like to talk, so I'm going to shut up now, and I hope to see you around the rugby field very, very soon. Best to all of you.